This video is for Stat 110, Module 3, Part 3, and includes a discussion of the chi-square goodness of fit test. Okay, let's go ahead and get started then. So the case study that we're going to use for this example is the Boston Medical Center case study. This study was centered around the scheduling of elective surgeries over a 2-year time period. Scheduling of surgeries is an important component of patient satisfaction and healthcare management. In particular, consistency in the scheduling of surgery results in less cancellations and allows for optimal staffing to be obtained. So when we are scheduling these surgeries, we'd like to do those in a consistent manner. This study has two main goals, and that is to determine whether or not the number of elective surgeries is inconsistent in year 1. That's the data that we have shown here on the screen. And then the Boston Medical Center made a change to their scheduling of the surgeries between year 1 and year 2. And they wanted to see if things were better in year 2 after making those changes. So here's the data. Their data starts in September and goes through August. We have data every month and the number of surgeries that were done at this particular clinic. Again, the question is this statistically inconsistent? Is there enough evidence to say that surgeries are inconsistent? We're going to use a chi-square goodness of fit test for this analysis. So the research question, is there evidence to suggest that the number of elective surgeries are inconsistent throughout year 1? We actually have a total of 12 parameters for this example, one for every month, starting in September and ending in August. The research question was asking whether or not the surgeries were inconsistent. So the null hypothesis is going to be set up under a situation of no difference again. So that would imply that the surgeries are consistent throughout year 1. Remember, what we would like to show, the research question goes into the HA. The null hypothesis is how the reference distribution is built. If surgeries are equal across all 12 months, then I should expect about 1/12, which is 8.33% in each month. So that's going to be the value of the parameters under the null hypothesis. So here I have the data in a spreadsheet, just listed out across with the observed values. I also created a segmented bar graph here. There's a separate video provided that shows you how to create those segmented bar graphs. We have 2 questions right away, so I'll let you go ahead and hit pause and answer these questions. Okay, computing the expected quantities then. The expected quantities is just going to be the total number of surgeries for that particular year, which is determined to be 429. And then I need to multiply that by each of the parameter values that are in the null hypothesis, which is that 1/12 again, or that 0.0833%, or 8.33%. As a decimal, it would be 0.0833. So doing that math, I get an expected count of 35.75. And that's going to be the same for all months. Once I have the observed values and the expected values, I'm able to conduct my chi-square test. Again, I have a separate video that goes through and shows you how to actually do this test in Google Sheets. And the process is exactly the same in Excel. So in Excel, it is also the chi-test function that will return the p-value for this analysis. To do this, all I need to do is simply type equal chi-test, parentheses. I need to specify the range for the observed values, which in this spreadsheet go from C3 through N3. I need to put a comma in there, so I have a comma between the observed and the expected. And then I just highlight the range for the expected counts as well, which are C4 through N4. The value that's returned by the spreadsheet is the p-value for the test. So now I'm able to complete the test. The p-value is 0.0567. Is that less than 0.05? Technically it is not, but notice that the p-value is very close to that 5% threshold. So technically speaking, we do not have enough evidence for the research question. And the conclusion would be stated that way as well. However, the Boston Medical Clinic went ahead and decided to make a change in the scheduling between year 1 and year 2 because this p-value was very close to that 0.05 threshold. Recall, if the p-value was 0.04, then we would have enough evidence to say the surgeries are inconsistent. So the Boston Medical Clinic didn't use that strict 0.05 rule. They went ahead and made a change even though the p-value was slightly above the 0.05 threshold. One thing that you can do with the chi-square test is compute the quantity of observed minus expected squared divided by expected. We did that earlier in part 2 of this module. Now, one advantage of doing that is that you can see which cells or which categories are really far off from the expected. And we call this idea the cell contribution. We can see that February deviated a lot from the expected. And that contributed a lot to the test statistic value of 19. So it looks like almost half of the test statistic is due to February. Other months that contributed a lot are July, September. Those are cells in which the observed and the expected were far apart from each other. There are online apps that you can use to conduct this test. I've just provided one here as an example. This online app also requires you to enter the observed values and also the expected values, just like our spreadsheet. This one here just generically needs labels for the different categories. I just labeled those the 12 months. You click Calculate Now, and you can see that the test statistic is returned, the degrees of freedom are returned, and also this notion of the p-value as well. So the p-value should be the same that we computed here in Excel, which was 0.0567. Let's talk about then example 3.3.2, which is from the same organization, except now I'm looking at data from year 2. So this is after they made their change to their scheduling process. They are hoping that these data here are more consistent than what we had up above. What I would need to do to compute the p-value is again simply enter the observed numbers, which are 43, 48, 31, all the way down here. I'm going to have a different total for this year, 463 surgeries in this year. So that means I'm going to have a different expected quantity. So you're going to need to take 463 times that 1/12 for year 2. And it looks like if the surgeries are occurring equally, then we should see about 38 or 39 each month. Or technically 38.58 surgeries each month. The p-value is obtained using the chi-test here, and it's 0.43 if we round. Recall that the p-value for year 1 was much, much smaller at 0.0567. So this p-value here is not even close at all to that threshold, which implies that there is not enough evidence to say that the number of elective surgeries are inconsistent in year 2. Now, practically speaking here, the p-value from year 2 is considerably larger than year 1. So there definitely was an improvement in the consistency of the surgeries between year 1 and year 2. So the money spent on this new program was worth it here for that particular clinic. All right, let's look at another example. This is the Minnesota Student Survey data again regarding substance abuse. And here I'm looking at smoking marijuana once or twice per week. I'm going to again look at grade 11. And I'm going to do females and males separately. So the research question here to begin with is for grade 11 females. Is there evidence to suggest that the perceived risk from smoking marijuana for grade 11 females from Fillmore County tends to deviate from the historical rates of other grade 11 females from the state of Minnesota? In order to conduct a chi-square goodness of fit test, I need to give you what the data values need to be compared against. And here those historical rates are about 60% tend to split evenly between great and moderate risk. So that would be 30% in each of those categories. And the remaining 40% tend to split evenly between slight and no risk. So that would be 20 in each of those. So in this example here, all of the expected proportions are not the same like they were above. To get the expected counts, I just need to take the total again, 64, and multiply that by 0.20. That's 12.8. That's going to be the same expected for the no risk and slight risk because the expected proportions are the same. To get 19.2, what I did is I took 64 and multiplied it by the 30%. I think I'm talking too much because that's the question that I had here for question 3. So I'll hit pause, go ahead and hit pause and answer question 3 and question 4. To complete the test, again, I just use the observed range, which in this sheet is cells C3 through C6. C3 through C6 here for the observed, and the expected are included in cells D3 through D6. The p-value here for the females is quite high, which means I do not have enough evidence for the research question, which practically is saying that the perceived risk of smoking marijuana for grade 11 females in Fillmore County tends to be similar to, or does not deviate from, the historical patterns for grade 11 females. The analysis for grade 11 males follows here. Is there evidence to suggest that the perceived risk from smoking marijuana for grade 11 males from Fillmore County tends to deviate from the historical patterns? The historical patterns here are just males tend to split evenly across those 4 risk categories. So with the legalization of marijuana in several states, we have an equal number that believe that it's no risk, light risk, moderate risk, and great risk. Years ago, that might not have been the case, but now historical patterns are pretty even across those. Here's a comparison of the stacked bar graphs. We can see that for the observed count, we have 25 individuals at grade 11 from Fillmore County that took the survey anyway. 25 of those 61 thought smoking weed was of no risk. The expected count should be about 15. So that seems quite a bit higher than that expected count. On the upper end, I don't have as many in that great risk as I would expect. So here, go ahead and show me the analysis for the chi test for the males. You should be able to download the spreadsheet here and do what I did above for the females. So I want you to just conduct the test as I've done here for the females. I want you to do that for the males here. Once you've done that, you should be able to complete the test here. So I got questions here about what the p-value is, do you have enough evidence, and then write your conclusion. A couple additional questions down here about scope of inference and what actions should be taken. So go ahead and give your best attempt at those questions. Again, after you submit the notes, you can see my solutions. Now, one thing that we did up above is we compared the grade 11 females to their historical trends, and we compared the grade 11 males to their historical trends. A more direct comparison of gender may be of interest. So in other words, just do a direct comparison between the grade 11 females in Fillmore County to the grade 11 males in Fillmore County. Now, this cannot be done with the goodness of fit test. Okay, we will learn more about this in Module 4. This type of test here, where I have more than one set of observed counts, is called a chi-square test of independence. And that is what will be considered in Module 4. So we cannot do this test here using a chi-square goodness of fit test. The other thing is that there's sometimes questions on surveys that are mark all that apply. So one on the Minnesotan student survey that was mark all that apply is the following. During a typical school week, where do you usually get your lunch? Students were asked to mark any of those that applied. In this type of question, the percentages are going to be, or could exceed 100%, because students are allowed to select more than one category. Again, a chi-square goodness of fit test cannot be used with this type of data. One restriction is for a chi-square goodness of fit test that the percentages all add up to 100%. Okay, then that does it for Module 3, Part 3, the chi-square goodness of fit test. Thank you.